Here we're going to fill in a table that contains information about either isotope symbols, numbers of protons, numbers of neutrons, or numbers of electrons, filling in any missing gaps. In order to fill out the rest of this table, we're going to need to know the relationship between protons, neutrons, and electrons that make up a particular type of substance. Know that protons always identify a substance, and we distinguish unique elements based solely upon the number of protons their nucleus contains. For example, in the first row, we're given the isotope symbol that's got an element lead. Lead will always have the same number of protons no matter which isotope or ion variation it's in. And we can find the number of protons from the atomic number listed on the periodic table. The atomic number of lead is 82. So we know that no matter what version of lead we're dealing with, we've got atomic number 82. And lead has 82 protons in its nucleus. So we can always identify numbers of protons straight away, or use the number of protons to identify the element's identity. To get numbers of neutrons, we're going to have to take into consideration the mass of a particular isotope. The mass of an isotope, recall, is equal to the number of protons plus the number of neutrons that the nucleus of that isotope contains, as protons and neutrons contribute to mass. We can always find mass in an isotope symbol as a superscript off to the left-hand side. For instance, in the very first isotope we're interested in, lead-207, we know that the mass is equal to 207. We now know how many protons this lead isotope's nucleus contains, so if we want to figure out how many neutrons there are, we just subtract 82 from 207. For this lead isotope, we should identify that its nucleus contains 125 neutrons. As far as numbers of electrons are concerned, for electron count, we must take into account charge. The overall charge on an ion is due to numbers of protons minus numbers of electrons, because protons contribute +1 for a charge, and electrons contribute -1 for a charge. The charge of an ion is given as a superscript on the right-hand side, along with a symbol that identifies its sign. In this case, that charge on our lead ion is 2+. In the first case, 2+, or +2, must equal the number of protons that our nucleus contains minus the number of electrons surrounding the nucleus. To solve this, we'll rearrange our equation and subtract 2 from 82. There must be 80 electrons around this nucleus. Another way to think about the number of electrons is that because electrons are negatively charged, anytime we have a cation, cations are positively charged, and we can remember that because there's a big plus charge in the center of the word, we must have fewer electrons than we do protons. How many fewer? In lead's case, 2 fewer. For our next example, let's expand the board. We need to write out an isotope symbol. We can identify our element based on the number of protons its nucleus contains. This nucleus contains 24 protons. The only type of element that can have 24 protons in its nucleus is chromium, atomic number 24, symbol Cr. The mass of this particular isotope of chromium is due to a combination of protons and neutrons in its nucleus. There are 24 protons and 28 neutrons, and combined, they contribute a mass of 52 to this isotope. Therefore, this chromium isotope must have mass number 52. there are 3 fewer electrons than there are protons in this ion. If there are 3 fewer electrons, there are 3 fewer negative charges. So positive charges went out. This must be a cation with 3 more positive charges than negative charges. Overall, the isotope ion symbol for this substance is chromium-52 with a 3+ charge. For our phosphorus ion, in the next example, we'll look to the periodic table once again to find number of protons. Phosphorus is atomic number 15, therefore its nucleus must contain 15 protons. The mass number of this particular isotope of phosphorus is shown in the upper left as 31. The mass number is the number of protons plus the number of neutrons, so the mass number minus the number of protons must give us our number of neutrons. 31 minus 15 is 16. The negative charge on this ion indicates that there must be more negative charges, or electrons, around the nucleus of this atom than there are protons in the nucleus. There are 3 more electrons than there are protons, according to this symbol. If there are 15 protons, that must mean there are 18 electrons in this ion. For selenium-79, notice that we don't have any charge at all. That must mean that this substance is electrically neutral. In other words, the number of protons and the number of electrons are perfectly balanced. The number of protons in selenium is 34, because selenium is atomic number 34. Because charges balance between positives and negatives, there must also be 34 electrons. To determine the number of neutrons, we subtract 34 from the mass number 79. 79 minus 34 is 45. There must be 45 neutrons in this isotope. Lastly, we're given information about number of protons, number of electrons, and a mass number without an element symbol or a charge. We need to determine information to fill in the blanks here and here, and we need to deduce the number of neutrons in this substance. Once again, start with the easiest thing. The number of protons identifies an element. Element with atomic number 80 is mercury, symbol Hg. This isotope of mercury has a mass number of 201. We can determine the number of neutrons by subtracting from the mass number the number of protons. 201 minus 80 is 121. There must be 121 neutrons in this isotope of mercury. Lastly, we can fill in a charge, the thing that fills in the upper right-hand superscript, by comparing the number of protons with the number of electrons. There are 2 fewer electrons than there are protons. The positively charged protons went out. There are 2 more protons than there are electrons. So this mercury ion must have a 2+ charge.